Okay, welcome to this video, which is a video that will describe the current divider. The current divider is a way of analyzing circuits where you have two parallel resistors and you want to find the current that's flowing through each of those resistors. And it can be quite useful in certain situations. So to introduce it, let's begin with a circuit that looks like this. I have a current source, and for the sake of an example, we'll say that's 3 amps. And that current source is connected to a 1 ohm resistor and a 2 ohm resistor that are both in parallel. Okay. So the goal in using the current divider is we want to find the current that flows through the 1 ohm resistor and the current that flows through the 2 ohm resistor. Now it turns out what happens is the 3 amps that flows out of the source, out of this guy, splits, and some of it will flow through the 1 ohm resistor and some of it will flow through the 2 ohm resistor. Unlike what you might think, it turns out that many people will assume that the current splits evenly between the two resistors. But because the two resistors have different values, it turns out that the current through the 1 ohm resistor is larger than the current through the 2 ohm resistor. Current takes the path of least resistance, or at least more current takes the path of least resistance. So what we'd like to do is figure out exactly how much current flows through each resistor. We do this by using the single node pair analysis that was done in a previous video. And to do that analysis, we label the two nodes voltage, which we don't know yet, as V. And again, those of you that have seen me do this now 5 or 6 times are probably sick of it, but just to remind you, this whole thing is one node. This whole thing is one node. So the voltage across the two nodes we will label V. And from the single node pair analysis, we discovered that V is equal to 3 amps over 1 ohm plus 1 over 2 ohms. Okay. Now, we also can write the currents that we're interested in terms of V. I1 is equal to 1 ohm. Whoops. Let's not do that quite so quickly like that. It's the voltage across the resistor V, which we've just solved for, over 1 ohm. Okay. I2 is V divided by 2 ohms. And we can use the fact that we've solved for V. We now have an expression for I1 or I2 to figure out what I1 or I2 is. So let's start with I1. We have I1 is V, which in this case is 3 amps over 1 ohm plus 1 over 2 ohms. And this whole thing is divided by our 1 ohm. Okay, how on earth are we going to do this? Well, that's actually a good question. Basically, another way to write this is 3 amps over 1 ohm plus 1 over 2 ohms times 1 over 1 ohm. So what I've done here is basically divided the voltage by this resistor by writing it this way. And the next thing I want to do is take this denominator and basically take these two fractions, put them over a common denominator, and then invert it, and that will actually then lead to the answer I want. So if I just look at these two guys, I have 1 over 1 ohm plus, we'll go back to the hot pink here to represent the 2 ohm resistor. Okay, so what I want to do then is multiply top and bottom of the 1 over 1 ohm by 2 ohms. And multiply top and bottom of the 1 over 2 ohms by 1 ohm. And when I work this out then, I end up with an expression that looks like this. In fact, here we'll move this over here. I get 2 ohms plus 1 ohm over 1 ohm times 2 ohms. Okay, so basically that's what this guy here looks like. So I'll clear out a little space here to finish up this computation. So with this result, I have I1 is equal to 3 amps times 2 ohms, 2 ohms times, here, let's do this a little tidier, times 1 ohm times 2 ohms. So basically I'm dividing now by this expression, so that's the same as flipping it and multiplying. 2 ohms plus 1 ohm, and then I still have this guy over here, which is the 1 over 1 ohm, which then simplifies. These two guys cancel, and I'm left with 3 amps times 2 ohms over 2 ohms plus 1 ohm. Okay, that was a mess. But it turns out that we can now go back to our circuit diagram and interpret this in a way that's useful. So the current going through this resistor, I1, is the current coming out of the current source. That is, and this is the current that will go through both resistors. Well, it'll either go through one resistor or the other, and the sum of the currents going through the two resistors is 3 amps. So it's this current times the resistance that the current's not going through over the sum of the two resistors. So that's a very handy result. In this case, then, we can have I1 will be 3. Oh, wait. Boy, I don't know why, but I find current division harder than voltage division. And the concepts are actually so similar that it shouldn't be. So it's 2 ohms over 2 ohms plus 1 ohm times 3 amps, which in this case turns out to be 2 amps. Okay, so that was kind of a painful derivation, but again, I don't know why it's that hard. It shouldn't be. So let's clear out a little bit of space and do I2, and we'll just use the pattern that we've noticed. I2 will be 3 amps. That's the current flowing through the parallel combination of the 1 ohm and 2 ohm, times 1 ohm, that's the value of the resistor that the current's not flowing through, over 1 ohm plus 2 ohms, which turns out to be 1 amp. So what we see is that the more current, 2 amps, flows through the smaller resistor. Less current, 1 amp, flows through the larger resistor. The amount of current that flows through each resistor is not the same. It would be the same if the two resistors had the same resistance, but since they don't, it's not the same. So that basically gives us the current divider. And what I'll do now is rewrite it in a nice tidy form to make sure that it makes sense. So I have some current here, which I'll just call I. I have a resistor R1 and a resistor R2. And if I want to know the current through the R1, I1 is my current times R2 over R1 plus R2. That's the current divider. Okay, now I'd like to leave it at this, but there's one misconception that shows up all the time, and I want to try to disabuse you of it. I want to say something like that's wrong, 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 because many of you will do this, and someone will have to tell you that. So let's suppose that I have 3 resistors that are in parallel, and I still want to find the current I1. The temptation is to look at the pattern we've already developed for 2 resistors and say, well, then I1 is going to be equal to the current plus, I don't know, maybe R2 plus R3, maybe because it's not flowing through these 2 guys, over R1 plus R2 plus R3. That is wrong. Wrong, 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 wrong. Okay. It turns out, and you'll see this when we start talking about equations for parallel equivalent, or the equivalent resistors to parallel resistors, that you really can't do the current divider easily or tidily with more than 2 resistors. If you have a 3rd resistor, you have to be a little careful. So, again, the point I'm trying to make is that for the circuit that we've drawn in yellow, for this part of the circuit, this equation holds, and it's very useful. When I add a 3rd resistor, I'm tempted to do something like this, which again is a very bad idea. So that concludes the video on the current divider. Thanks for watching.